the general formula for alkenes. Now, as we know, these substances can be linear or in a circle. So when you're talking about linear alkenes, those you write in a straight line like that, they've got the general formula CnH2n. You're also going to have, actually, this same formula that we are seeing here is also the formula for cyclic alkenes, those alkenes which are found in a circle. So meaning that if you are talking about alkenes which are also cyclic, because I've got a double bond somewhere, you can lack some hydrogens, and so you might not necessarily get to obey this formula which is here. So that is maybe something that we can take note of. Let's get to mention, maybe people can help us with the general properties of alkenes. What are some of the properties that we've read or that we know? Anyone to help us with some properties? Any property that you know? Any property of alkenes? Okay, one property that I can mention is the melting and the boiling point. So the melting point and the boiling point of alkenes is going to increase as you get to increase molar mass. And that is something that is direct. Like when the molar mass is getting to increase, you know you have got carbon bonded to hydrogen like that. So this bond here, they are what we call intermolecular bonds in alkenes, and specifically because carbon and hydrogen is a non-polar bond, so you expect to find London dispersion forces in alkenes because they are non-polar. But because of the double bond that exists between carbon atoms in alkenes, it makes them slightly polar than alkenes. So because of this, these are able to form much stronger attractions to each other. So because of that, the more you increase the number of carbons and hydrogens, the more you increase those intermolecular forces. So when you want to boil or to melt these compounds, what you do is you're actually breaking those intermolecular forces. Now for you to break those intermolecular forces, you would need a lot of energy. So the greater the molar mass, the greater the energy that you need to break such intermolecular forces. That is why the melting point and the boiling point of alkenes is getting to increase with increase in molar mass. Do we have do we have anyone who wants to get to add something or ask a question that we can get to tackle? Or we are moving together. Please be free to open your mic and be able to speak. Doc Maxwell, are we good?
Yes, dog, we are together. We can go ahead.
Okay. Now, uh, these alkenes, they are, when you are comparing them to alkenes, remember, because they've got a double bond between the carbon atoms, this double bond is going to make alkenes a little more behave as though they are charged. Okay, because you have got a pi bond on the double bond. So it behaves as though it is a bit of charged. So another property is that they are slightly soluble. You know that a bond between carbon and hydrogen is supposed to be a non-polar bond. Okay, and non-polar compounds cannot dissolve in water because water is polar. But because of a double bond that exists in alkenes, they are slightly soluble in water in comparison to the alkenes. I mean, the double bond gives these a partial positive charge. The double bond is going to give the alkenes a partial positive charge. All right. Are we still together? I'm seeing my network is becoming a bit of slow, so please, if it becomes like it's tripping like that, you can't hear, you can just go on and speak that you can't get, because Rins has got bad network. I'm okay, or is cutting that side? Yes, yes, my Doc Abigail. Is it okay? Okay, thank you. All right. So now, when you get to talk about alkenes, something that we can just get to mention about alkenes, remember one carbon is going to have a double bond. So you have got a double bond, and you know that carbon can only form four bonds. So meaning that it is just having two more bonds to form those four bonds like that. Now, who can help us, docs? What would be the hybridization of this carbon? When an atom is bonded to three other substances, what would be the hybridization? Yeah. Okay. So this is going to be S. Thank you. This is going to be sp2 hybridized because we are bonding with three different things. So for sp2 hybridization, the bond angle that you find is 120 degrees. And because we have got the three things, you don't have a lone pair. The geometry about each carbon with a double bond is trigonal planar. So this is the geometry that is in alkanes. Trigonal planar. On the alkane, I mean on the carbon that has got a double bond. Another thing that we just get to take note of alkenes is that depending on the side where you have got the substituent groups, it can either be cis or trans. So if you have got a carbon bonded to another carbon, and then this side you have got a group of carbons, let me call it, let me just say R. Okay, there is a question to say, does it mean the double bond increases the electronegativity between the carbon atoms? Do we have anyone who is going to be able to help us with that question? This double bond which is here, which makes uh, this bond partially positive, does it increase the electronegativity or something? Anyone who can get to help us with that question? So no one is willing to say anything. The doc was asked. We can more think of it in that way because you know that the bond between a carbon and a hydrogen is supposed to be non-polar. But the result of a partial positive charge, again, if you think of it, because these are all carbon atoms, meaning they've got the same electronegativity. So the partial positive charge is coming about because of the pi bond that is formed from here. I wouldn't say necessarily it's going to increase the electronegativity, but if it does, then it would be true. But what we can say is the pi bond which is present in this molecule is what gets to increase. I mean, is what gets to bring about the partial positive charge, meaning that the partial positive charge, we can think of it in this way. You know that carbon is supposed to form four bonds, right? It's supposed to form four bonds. But now in this compound, carbon only has got three bonds. What does that mean? The positive charge, remember, is supposed to attract electrons. So meaning that it is ready to attract another pair of electrons, which is going to come and attack, so that you are going to have now four bonds, because this one we are going to take it like it's reacted to one compound. So carbon wants to have to reach saturation to react with four things. So in other words, this appears as though it doesn't have enough electrons because it's bonded to three things. That's why the partial positive charge. Otherwise, if it's bonded to four things, then it is going to be okay with the charge that is going to have. So when we get again to look at alkenes, you see you have got R groups on the same side. Now when we say R, these are alkyls like methyl, ethyl, isopropyl, all those. When those different groups are on the same side, this we are going to call it as the cis configuration. And when you've got a double bond, let's say you have got the R here and then the R2 here, and then the hydrogens are like that. So you can see that the R groups are on the opposite sides. So what you consider is this point, okay, where the double bond is. So that is what determines the opposite side. So since they are on the opposite sides, this is going to give us the trans configuration. Can someone help us? Between the cis and the trans, which one is going to be more stable? And what would be the reason as to why that is stable? Anyone who can open their mic and Doc John, you can just get open the mic and be able to speak. Y-
I think the trans.
yes. What? Okay, trans. What would be the reason for as to why the trans is much stable?
I think when you come across them, it looks they're like balanced.
Okay. All right. Do we have anyone else who wants to make a contribution as to why the trans is more stable than the cis? Okay. Another, what we can give as a reason here is if you look at trans, these alkyl groups are further away from each other. So it's more like, these contain electrons, and electrons get to repel themselves, or they get to these compounds, the R groups, because they are big, they are going to be more like offering obstruction to each other. Okay, the less the distance between them, the more unstable because of, like, it is standing in the way of the other one. So the more distance the alkyl groups are from each other, the more stable. That's why the trans isomer is much stable than the cis because of that. So trans isomers are stable. Okay. We can also talk about stability when you're talking about not just trans and cis. So when you're talking about, you call them substituted or substituted, let me use that, substituted alkenes. So substituted alkenes are more stable than less substituted alkenes. More substituted alkenes are more stable than less substituted alkenes. That is also something that we need to take note of. And these questions, I've seen them to say identify which one of the following is going to be stable. Let's say you have got an alkene like this, which has got all these atoms which are bonded to that carbon with a double bond, are not hydrogens but alkyl groups. This one is going to be more stable in comparison to having only three of these hydrogen substituted. Let's say this fourth one is a hydrogen. So this is going to be, the first one is more stable than the second one because it has got more R groups. So the more the R groups, the more stable the alkene is going to be. And this is going to be more stable than this. Let's say you have got a hydrogen here, a hydrogen here, and then the other group there, the other group there. You can see this is not cis. When you're talking about cis, the point you talk about, this is the line you consider if the arrows are on the same side. So you not call this as a cis. Okay, and this compound we are saying is going to be more stable than the trans, where I've got ara here bonded like this, and then you have got hydrogen here, you have got ara here, you have got hydrogen here, and we know that the trans is more stable than the cis. The cis is the one with ara groups on the same side. And the cis also is more stable than a monosubstituted alkene. What we mean by monosubstituted is that it has got only one R group, the rest are hydrogens. That's a monosubstituted. And this one is also going to be more stable than a non-substituted alkene. Non-substituted means everything are hydrogens. So the most stable alkene is the tetrasubstituted, meaning that all the four hydrogens have been substituted with the R groups. The second is the trisubstituted, and then you have got this one, which is the disubstituted, and then you have got the trans, cis, and then monosubstituted. The least stable is the one which is not substituted at all. Docs, do we have anything to say on that? Yes, Doc Maxwell.
I'm sorry, Doc. I just want to know why the tetra is more stable than the others.
Okay. Why is the tetra more stable than these others? Do we have anyone who can give us, maybe who can try to help us with an explanation for that? Anyone who can help us? Hello, docs. Why do we think the tetra substituted is more stable? Yes. Oh, yes.
Yeah, maybe I put it this way because you said that the most substituted alkene
Yes.
they are more stable than the ones that they are rest. Now
Yes.
they are more substituted this, and which makes them to be more stable. That's my question.
Okay. Yeah. Yeah. Do you have anyone who can help with that? Okay.
Me,
Yes, doc.
I think I think they're more stable because when there are all our groups around, they have the same force. It becomes like stable already. I really don't know how to explain it.
What of the last one, because they are all hydrogens? What would you say about that?
They are stable, but not compared to as the substituted ones.
Okay. So you can think it more like that. And when you are talking about the stability of these, remember these form cations. when undergoing reactions, they are going to form some positive charge. So when you have got these R groups, there is what is called there is more like sharing of the charge. There is a sharing of the charge that gets to happen. So when you have got a lot of R groups, the charge that is going to be formed as an intermediate when the reactions are happening is going to be shared by the R groups, in comparison to when you have got only hydrogen, because hydrogens will not be able to share that charge which is going to be seen as an intermediate when a chemical reaction is happening, because we are going to be discussing reaction mechanisms. And for a mechanism, you have got E1 reactions where you are going to first form a carbocation, and that has to be stabilized. The charge has to be stabilized. So when you have got these a lot of R groups, the charge is stabilized by a lot of R groups. In other words, the charge is going to be shared between the different carbon atoms. I don't know if that is a bit answering the question. Doc Maxwell. All right. Now, something that we just need to take note of before we do some questions on determining which one is going to be more stable is that when you have got these alkenes, alkenes generally are going to act as nucleophiles. Nucleophile means nucleus loving. So these act as nucleophiles. They are going to attack uh, acids. Okay, they are able to attack acids. And what is going to happen is that basically this one is a strong acid. We can also say alkyl halides can be attacked. So this double bond here is able to go and attack this hydrogen which is here. And when that happens, this hydrogen is going to be grabbed. So this bond is going to be broken. The two electrons are going to be taken by this atom. The reason as to why this atom is taking these two electrons is because this atom is more electronegative than hydrogen. You can think of chlorine, hydrochloric acid, because we are saying this is a strong acid. And the result is that you are going to have this double bond breaking, and then you are going to have a compound like this. Okay, and then now the A has gained those two electrons. So because it has got now an extra electron, it carries now a negative charge because it has got more electrons. So these compounds, they get to form, I mean these alkenes get to act as nucleophiles. Now remember, this nucleophile has only gotten one hydrogen. And for each carbon is supposed to have, because here it only has four hydrogens. So each carbon in this, if you want to form an alkane, is supposed to have three hydrogens. So where is the other hydrogen going to come from? So what you are going to see is because one of these carbons, like one hydrogen, is going to carry a positive charge. And that is why this carbon is going to be called a carbocation, because it lacks an hydrogen and so it carries a positive charge. The carbo just means carbon, cation, we know that is a positively charged ion. So that is what gets to happen here. Okay, let's identify some compounds to see which one is going to be more stable than the other one. We should also try to give reasons as to why it is so. Let's compare this one with this one. Docs, who can help? Which one is going to be more stable between these two? Which one is going to be more stable? Doc Maxwell, why is the second one more stable than the first?
I think when carbohydrates could act as because it's not the case of the carbon.
Okay,
That makes electronegative against
okay.
alkene.
Okay, thank you so much. Do we have anyone else who can help us? Why is the second, or maybe which one is going to be more stable from others between these two? Anyone? Anyone? Between 1 and 2. Yes, yes, Doc. What's what?
Like from the way I'm seeing this, is the second one is more stable because when you see that compound, it can form two products,
Okay.
which is the double bond can be on the like the way it is, the first one, which is the way it is. Then the second one, the double bond can be on the which is the tertiary carbon. So
Oh,
it is more stable because uh, the double bond, according to alkenes, they are more stable on the 3 degrees than on the primary, which is the 1 degree.
okay. Thank you so much.
You're welcome.
Okay. All right. So, just as we have said, maybe just to make it a bit more clearer, when you are talking about the stability of alkenes, you are going to consider where the double bond is. So, what you are going to do is look at the double bond and look at the substituent groups. Okay? So, if you consider the first one, where the double bond is, at the beginning here, you don't have any substituent, you only have a hydrogen. Okay, meaning that you only have this substituent. Substituent, you're talking about carbon chains, and then you have got this substituent. So, meaning that for the first one, you only have two substituents, right? And then for the third one, consider where the double bond is. The first substituent is here 1, the second one 2, the next one 3. You have got three substituents. And we said the more the number of substituents, the more stable the alkene is going to be. So thus, this alkene is going to be much stable than the first one. So you can also explain when you talk about the kind of carbons where they are attached to, okay, like that. But more you get to explain considering the number of substituents. Okay, let's consider another pair. Which one do we think is going to be more stable when we talk about this? So let me say this is 1, this is 2, and then this is 3. Which one do we think is going to be the most stable, followed by which one, and which one is going to be the least stable? Anyone? Docs, who can help with this one? Yes, yes, Doc Oswald.
I think the most stable is one, then followed by three, then the last one should be two.
Okay, 1 followed by 3, and then by 2. Okay. So we can basically determine the number of substituents. The first one, it has got on the double bond, the first substituent there, second, third, fourth. So it has got 4 substituents. The second one has got only 1, 2 substituents where the double bond is. So this one has got 2. And then the third one, it has got 1, 2. Okay, the third one is here. So it has got 3 substituents. So that is going to give us the most stable is the first one, followed by the third one, and then the second one. So I think we are now good with determining the stability of alkenes. So that is how we are going to be able to look at them. Do you have any question or anything?
Yeah, Doc.
Yes, Doc.
Probably, I just want to be clear on how to see that these are what is the most substituent, the most substituent.
Okay. So we are going to look at where the double bond is. if we get to identify the double bond now, consider everything that is attached to the double bond apart from hydrogen. What other groups do you have? So we can see we have got this part, we have got this part, we have got this, and we have got this. All these are attached directly to the double bond. If you consider the second one, you only have this part which is direct bonded to the double bond, and then this part. If you consider the third one, you have got this part is direct bonded to the double bond, this one, and also this part is direct bonded to the double bond. So those are going to give us the substituents.
Sounds clear.
All right. Anything else? Okay. If there is nothing else, let's consider how do you get to prepare alkenes? Like how do you prepare alkenes? So the first method of preparation of alkenes we can be able to discuss is acid catalyzed dehydration of alcohols. Now we know that dehydration is what is dehydration? What is
Removal of water.
the removal of water? Thank you. So when you want to prepare alkenes, you are going to remove water from alcohols using acids as catalysts. So that is the first method that we get to use. Let's say if we have got this alcohol, who can help us with the name of this alcohol? Sorry that it is not shown just now. Okay, there it shows. Who can give help us with the name?
Ethanol.
Okay, ethanol. So thank you. So here we have ethanol. It has got two carbons, so that's ethanol. So when you get to to break this compound by removing water using an acid, okay? Let's say we are using concentrated sulfuric acid or hydrochloric acid, phosphoric acid. Let's use sulfuric acid. Now, basically what happens is that this sulfuric acid is going to provide hydrogen ions. So you are going to have an hydrogen ion. And this hydrogen ion is going to come and attack the OH group. And when that happens, you know that actually this oxygen which you are able to see with the hydrogen has got two lone pairs of electrons like that. So this hydrogen is going to come and attack this oxygen. Now oxygen cannot have all these many bonds because when the hydrogen gets to come there, you are going to have more than the required number of electrons. So that is going to make this bond between oxygen and the alkane be broken. So I'm going to break that bond. So when that bond goes there, see you only have two carbons. That is going to form a double bond there. And then you are going to have water as a product. So the corresponding alkene is going to be formed. Since you have ethanol, you are going to have ethene as a product. So this is basically the reaction that gets to happen here. Are we okay?
Sorry, can you just repeat on the part of the formation of ethene from the ether?
Yeah, so the proton that is coming from the acid, remember this is an acid catalyzed reaction. So the proton that is coming from, I don't know if you are able to get me. Are we able to get me? All right. So the proton that is, or the hydrogen ion that is coming from the acid is going to attack the hydroxide that is attached to the alcohol, the functional group. And that is going to make the bond between the alkene and the OH be broken. And so that is going to form a double bond leading to the ethene. Maybe we can give another example for clarity's sake. So let's say we have got, we can have this one. Yeah, please pardon me, I've just lost the network. Yeah, just a moment. The PC just disconnected. I don't know if we are able to see now. Are we able to see?
Yes.
I don't know, Dorcas, did you get what I said before? On the question that you asked, did you get what I said? Okay. All right. So let's get to look at this one. We got to consider another example. I don't know. The network has just started behaving. Yeah, they just started behaving. I wish I wasn't at ruins. But if we get to shift to Ridgeway, to be much better because I believe we are going to be in nice places. Ruins, the network is bad. Just give me a moment, I try to reconnect. Network chavota. It's a big disappointment. All right. It's so unfortunate with our network here. We hope it will be better as we get to go on. Is it now settled? Are we now able to see? Okay. Okay, let's try this alcohol here. What would be the name of this alcohol? Who can help us with the name?
butan, it's propan.
It's Doc. Can you say that again?
Propan.
How many carbons does it have? Yes, Doc Oswald.
It's butane.
Butano. Okay, so it has got four carbons. So,
I think it's state butane. Butane.
okay, tet butano. Or we can say we can say 1, comma 1 dimethyl. Now, if we use that one, then we are going to consider this one as one carbon, carbon 2 there. So this is going to be 1, comma 1 dimethyl ethanol, or the same 30 butano. Okay. So same with this, the hydrogen ion that is going to be provided from the acid comes and attacks this. When that gets to happen, the bond here is going to be broken. Okay? Sorry, not where I'm showing. The bond is going to be broken here, and then the double bond comes and attaches at this point. So what you are going to have is a double bond here, and then you have got this, and then you are going to have your water as a product. So this is what gets to happen. So now we have got a result which is shown here. Now the name of this is 1 carbon number 1, carbon number 2, carbon number 3. So we would say this is 2-methyl prop 1N. 2-methyl prop 1N, or 2-methyl propene, I mean. 2-methyl propene. Now, because we are considering, for this one, you don't even need to put the position of the double bond, because at whatsoever point that you put the double bond, it will still be the same, because the double bond the double bond can actually just be where it is, or it can come here, it will still be the same name. Okay, so this is how you get to prepare alcohols using this method of acid catalyzed dehydration of. That's how you prepare alkenes, with acid catalyzed dehydration of alcohols.
Excuse me.
Yes, please.
Which one is the nucleophile in that case?
Okay. So the nucleophile is always the one which is seeking the nucleus, going towards the nucleus. In other words, attacking electrons. So you expect this, the acid, to be the nucleophile. It's going towards the nucleus. It loves the nucleus. That's okay?
Yes.
Okay. So when you are talking about this same dehydration, it is going to usually form carbocation intermediate. That is when you are talking about an E1 reaction. Now, E is just meaning elimination. So elimination first order reaction, just like the SN1 forms a carbocation intermediate. So same with this one. So alcohols that form stable carbocations do actually easily dehydrate, or they easily lose water. And the stability of the carbocation, remember we talked about the stability of the alkenes basically formed. Okay. So when you are talking about these stabilities of the carbocations, we have got carbocation and carbanions. Let me just mention them. It will be to be important in this discussion. So for carbocations, the most stable are those which are tertiary, followed by the secondary, and then followed by the primary. But for carbanions, meaning that they've got a negative charge, it changes. The most stable is this one, followed by the secondary, and then the tertiary. Maybe we can take note of that because we are going to be seeing reactions getting to happen with this which we're able to see here. So alcohols that form stable carbocations easily dehydrate. So meaning that those which easily dehydrate are the what? Tertiary carbons. Okay. So a more substituted, now that word is making me fail to pronounce, substituted, a more substituted alkene is the major product. Now we're going to talk about that, don't worry, because we have to mention something about that. We are going to see the name. Okay, so this is the first name, this is the first method that we can use to prepare these alcohols, I mean these alkenes. Now when you are talking about these preparations, you are going to involve two reactions. You have got the E1 and the E2 reaction. Now, to just introduce that before we go into even much detail of what we are talking about, just to introduce that because it will be very important as we get to discuss it. Let me just give a simple example now. I'm not using an alcohol, I'm using an alkyl halide. Let's say you have got this alkyl halide like this. You have got a chlorine attached here, and you get to react to okay, you get to perform a reaction in the presence of water, and you need to heat this because you know these are alkanes. So this is an alkane, you need to a bit of heat it up. So what you are going to see, if you want to write uh, a mechanism of the reaction that is going to be happening, is that for E1 reaction, what we mean by E1, this is first order elimination reaction. For an E1 reaction, the first thing that happens is that this thing will first break off just by itself. Okay, it breaks off just like in SN1 reactions. The halogen is going to first break off by just itself. So when this breaks off, what is going to happen? We remain with this. Now because this one has got less bond, this carbon here, it's going to form a positive charge. So this is what we call a carbocation. And for this one, it is going to be a secondary carbocation because it has got two carbons attached on both sides. And then we have got also chlorine. So chlorine is also going to be formed with four lone pairs of electrons. So because of that, it has got a negative charge, but it has caused more electrons like that. Now the carbocation that has been formed with a charge here is going to undergo another reaction. Remember, this is a mechanism. These are the steps that gets to happen for this reaction to occur. Docs, I think today the network has just failed us. God willing, we can We can go on with the
with the
class.
class.
I wanted to say another day because the network is just misbehaving. Those who know ruins know this place better. Okay, let me pick it from here. I hope we got how we reached at this point. So the chlorine has just broken away from the alkane. So what is going to happen is that now the water, in this case, remember this is an E1 reaction. So this step which we are able to see, the first step, this is the slowest step, and so it is the rate determining step. That is why we call it E1. So in this reaction, we can see we don't have the participation of water there in the reaction. It's just the chlorine breaking off by itself. That is why the rate of this reaction, the rate of an E1 reaction, is only dependent on the alkyl halide. So it is just K multiplied by the alkyl halide. So it doesn't depend on anything else. That's why we call it a first order reaction. Okay, so when you have got this carbocation, it's now going to be able to react with the water. So we are going to get to mention this kind of reaction because it's a substitution reaction that gets to happen. So what happens is that where you have got a carbocation, you are going to consider the hydrogens. I mean, the hydrogens of the carbons, one carbon away from the carbocation, or one carbon away from the carbon which contained the halogen. So you have got, you know that you have got three hydrogens at this point, like this. And then you also have two hydrogens here, okay, like that. So what is going to happen is that this water molecule is going to come and grab one of these hydrogens. Now basically what happens is that it grabs the hydrogen that is on another plane. Since here the carbon was already removed, unless when you're talking about E2, that is when you're going to talk about planes. So this one is going to come and grab this hydrogen. So it can either grab this hydrogen or it will go and grab these two hydrogens. It can either grab this hydrogen or it is able to grab this hydrogen. You see how what is happening. So it can grab any of those. So because of that, you are going to have a lot of product forming because you are not just able to grab one hydrogen. Remember, you grab an hydrogen that is on a carbon that is away from the carbocation. So now what is going to be formed is this: when this attacks or grabs this hydrogen, the bond that this hydrogen has is going to break and come here. So that is going to result into something like this with a double bond at this point. Okay. Or when this goes and grabs this hydrogen which is here, this bond is going to break. Now the bond is going to go closer to where the carbocation is. So when this bond breaks, it will come here. It will come here. Please, it will not come on this one. Not on this one. It will go to near where the carbocation is. So when that happens, what you are able to form is depending with, because you have got two hydrogens here, depending with which hydrogen you have attacked, you can either form this or you are going to form, let me write that properly. You are either going to form a compound like this. Remember, this compound has got four carbons, so we are going to form a compound like this. So that leads you to forming the cis or the trans isomer. So basically this is what you are going to form. Now from all of these, using rules which are specified on the course outline, one of them is going to be a major product. So the first one is beauty 1N. The second one is trans but 2N. The third one is cis but 2N. So the first one is called the Hoffman product. And then these other two, these are called zesive products. And actually, recessive products are the most stable products. I hope we got that. Recessive products are the most stable products when you are talking about elimination reactions. Now, what is an Hoffman product and what is a recessive product? So, when you are talking about this thing called recessive product, a recessive product is was proposed by Zesiv, of course, himself, and he says that alkene formed in greatest amount is that which corresponds to the removal of the hydrogen from the alpha carbon having the fewest hydrogens. Okay, having the fewest hydrogens. So if you look at this carbon here, it has only two hydrogens. When you look at this carbon here, it has got three hydrogens. So the most stable compound formed is the compound that is formed from the removal of the hydrogen from a carbon that has got few hydrogen. That is the recessive rule. And that product is the most stable. Now again, we know that the trans is more stable than the cis. So they are going to ask you to identify or to draw the major product. So the major product is going to be this one, which is the trans 2-butene. Basically, recessive products are more stable. So Hoffman is the opposite of the recessive. Hoffman found when you get to attack the carbon having the most number of hydrogens or the or a primary hydrogen. Are we are we good?